Hey everybody, welcome back to R and Applied Stats. So I have my hockey project that I've been working along as we go here, and I want to go through the contingency tables and the test for independence that we're going to do here. So I actually have to say that I think this part of the project is probably the shortest one. There's not a ton here that you have to do. My hockey portion is actually a little challenging, mostly because my data wasn't very nice to begin with. Okay, so let me run you through how I'm going to do this here. So I'm talking about hockey and contingency tables. I've linked up my project with the project before. I've given some titles. Please give some titles, guys. Make your paper look nice when you knit it all together. The first thing I had to do, well, let's show you guys here. Okay, so I run my first cell, and then let's go ahead and print the data out and show you guys what the data looks like. So I'm just printing data here. And remember, it's data because I called it data above. All right, good. So when I print this, you notice that I have a ranking, a team name, average age, game played, yada yada yada. But if you look at all these, they're all numbers except for the team name, the X, and the team name is not really a categorical variable. It's a case descriptor. So I don't really have any categorical variables. So this is a little bit of an issue that I'm going to have moving forward in this project. But if you go back and look, I actually artificially made a categorical variable a little while ago. I had talked about power plays, opportunities versus opponents' opportunities. So I go through here and I'm going to assign that as an actual variable. I still am dealing with that one team that wasn't on the data, and so I have to do is NA. If there's an NA, go ahead and make it 0. So I do that assignment here. And then I make this other assignment where I ask if you have more opportunities than attempts, you get less or more, and I give it a new variable name called power plays. So you might have to do something like this. So let's see if we've done it right. There should be 31 teams, so it looks like there are 17 teams that had less. By the way, equal would go in the less, so these should be pretty balanced. But there are 31 teams in the league, so that adds up to 31. That's a good sign, right? I need a second categorical variable to do this project, to do a contingency table. I need a categorical variable on the top and a categorical variable on the horizontal. So I'm going to do Canadian teams. This season, you cannot cross the northern border with Canada, so the Canadian teams are all just playing each other, which actually means that they're guaranteed that 4 Canadian teams will make the playoffs. That hasn't happened in a long time. So I go ahead and do that. I go ahead and add, and I just did this, guys, by actually like copying and pasting all the team names until I had them all the Canadian: Toronto, Montreal, Calgary, Winnipeg, Ottawa, Edmonton. So I just copy and pasted. I called that category Canadian, and I said if true if they were in there, and then it was false if they weren't in there. And I did that with the exclamation point here, which not in data in this. Yeah. So I do another table here. We did this already, but I do another table here that's the power plays and the Canadian teams. So if you're true, you're a Canadian team. If you're false, you're a team from the US, and if you're less, you had less power play opportunities than opponents' opportunities, and if you're more, you had more power plays. So there you go. So I got Canadian and power plays. All right, cool. So let's do then my test for independence. So I'm going back to this first table about the power plays, and I'm going to run my test for independence. The test here is chi-squared.test. Pretty straightforward. You do have to pass the chi-squared a table. This second piece of the command here is not required. But what that says is that I assume that both of these should be 1/2. 1 divided by 2. Remember, C gives you a list, and then I divide it by 2, so it's like 1/2. And more should be 1/2. If you don't include this, you assume they're all equal. But if you wanted to do something crazier, like say 1 had to be, we wanted to have, 1/3 and 2/3, we could do that as well. So this would give you 1/3 for the first and 2/3 for the second. Let's leave it as each should be 1/2. When I run that test, I see I get a p-value that is very large, and a chi-squared value that is very small. So I am going to fail to reject my null hypothesis. I do not have evidence that there is much difference from 1/2 and 1/2. Even though 17 is more than 14, I don't have statistical evidence that they are drastically different, so I'm going to fail to reject my null hypothesis. So some of the cool things you can do with this chi-squared test, one of the things I suggest you do is this expected. The expected will tell you, well, actually, when we ran this chi-squared test, what we expected was you to have 15.5 teams with less and 15.5 teams with more. So on mine, I had 17 and 14. You could see that, there's no way to have 15.5, right? Either you're going to have 15 or 16 or maybe 17 and 14, right? So it's not terribly unreasonable that I would be off. So let's do one more thing. I always want you guys to do a visualization if you can. The way we would visualize something like this is with the bar plot. It's not terribly interesting, right? But it gives you a visualization here. So go ahead and do that, okay? Next, I'm going to move on and I'm going to look at the contingency table, the two-way table. Now I'm going to look at the power plays and the Canadian teams. So again, I run the chi-squared test, and you notice I didn't put the p-values this time. I didn't need them, so I just didn't do it. I don't suggest you stick them in there. You really don't need them. So here I've gotten a high p-value, 47%. I'm going to fail to reject my null hypothesis that these are independent. The null hypothesis is that they are independent, so I fail to reject that. And my chi-squared is low as well. We can run our expected, and we get some expected values here, 13.7 and 11, 3 and almost 3. When we look at this table up here, yeah, that looks about the same. That's why we're failing to reject this. Last thing I want to include here is the Mosaic plot, and I think the Mosaic plots are really beautiful. For me, I only had 4 categories, right? There's only 4 numbers that go in here, so there's only 4 pieces of the Mosaic plot. But each of these pieces of the Mosaic plot will correspond to this size. Remember, less was about 17 and more was about 14, so these are a little different length. And remember, false is a little bigger. So this table's like a little backwards, but each of these is representing the excuse me, the area in the Mosaic plot is representing how many teams had that. So it's a good visualization, right? Less and true was only 2 teams. Less and false was, let's see, sorry, I'm scrolling up. Less and false was 15 teams. And we can see that by their size. So the Mosaic plot is nice. If you have a lot of data, like I did in the Olympics, this didn't look very good. If you have a lot of categories, excuse me, not a lot of data, a lot of categories. And I went ahead and used the GG plot. You can get it colored that way too. I'm sure you can color this. I'm sure there's tons of options. I just wanted to show you guys the basics here. Okay, so I think this part of the project is probably the easiest one. It only took me 1 video to do it. Keep going, guys. You guys are doing good, learning lots of R, and hopefully making a kick-ass project. All right, keep working hard.